Hello. In the last lecture, we have studied about Gauss map and the differential of the Gauss map. So this differential of Gauss map, it is a self-adjoint operator. So in this lecture, we are going to study about uh, a self-adjoint operator and its properties. Let us begin. So let us take a vector space V and V is equipped with an inner product. A linear map A from B to B is said to be self-adjoint if inner product of ABW is equal to BAW for all BW belonging to the vector space B. Let us denote B BW equal to inner product ABW. So BW, it belongs to the vector space B. So B is linear in each coordinate. So B, it is a map from B cross B to R. So this vector space, let us take it over R. So B is a linear in each coordinate. And let us denote QB to be equal to B of B comma B. So which is again equal to, by the definition of capital B, it is inner product AB with B. So Q is called quadratic form on the vector space V. Okay. Let us first prove this following lemma. So if Qxy is equal to ax square plus twice b xy plus cy square, restricted to the unit circle xy belongs to R2 such that x square plus y square equal to 1 has a maximum at the point 1 comma 0, then the coefficient b is equal to 0. So what is the proof of this lemma? So let us take xy belongs to the unit circle. So then x equals to cos t, y equal to sin t for some t. Okay. And qt, so this is so let qt equal to q of cos t comma sin t. So this will be equal to a cos square t plus twice b cos t sin t plus c sin square t. And now we take the derivative of this q with respect to t. So this will be equal to minus twice a cos t sin t twice b cos square t minus twice b sin square t plus twice c sin t cos t. Okay. So this again it is equal to a minus c sin 2t plus twice b cos 2t. Okay. So at t equals to 0, okay, maybe I'll just so we want to yeah, so we have assumed that this q it is maximum at 1 comma 0. So at t equals to 0, so that is 1 comma 0, q is maximum. So therefore, so this dq dt at t equals to 0 will be equal to 0. And if I put t equals to 0 in this equation, so this will imply that b is equal to 0. So therefore, I have proved the lemma. Okay. So using this lemma, we have this following proposition. So given a quadratic form Q on B, there exists an orthonormal basis E1, E2 of B such that if B is given by B equal to X E1 plus Y E2, then QB is equal to lambda 1 X squared plus lambda 2 Y squared, where lambda 1 and lambda 2 are the maximum and minimum of Q on the unit circle W belongs to B such that norm of W is equal to 1. So this circle, it is taken in the inner product space B. Okay. So what is the proof of this? So let us take this lambda 1 to be the maximum of QB, where norm of B is equal to 1. Okay, maximum of QW, norm of W is equal to 1. So we don't have to take this thing. So this is given. So lambda 1 is maximum of QW, where norm of W is equal to 1. So note that this Q, it is a map from this B to R. So QB is defined to be equal to B, comma B, which is again equal to the inner product of AB, comma B. So Q, it is a map from this B to the scalar field R. Okay. So now, so there exists. So then there exists a vector E1 belong to the unit circle S1 such that Q of E1 will be equal to lambda 1. Okay, so why this is true? So Q, it is a map from this B to R, and we are restricting this Q on this circle So this Q quadratic form, it is a continuous map. And circle is compact, so therefore its maximum and minimum will be attained. Okay. And now let us take E2 to be a vector in the unit circle. So E2 belongs to S1 such that this E2 is orthogonal to E1. So inner product E2 E1 is equal to 0. Now let us take, so let lambda 2 is equal to Q of E2. Okay, so this V, it is a vector space, and this E1, E2, so these are orthonormal vectors of this V. So E1, E2 are orthonormal vectors of V. So here I have to assume one thing. This dimension of this vector space is equal to 2 because I'll be dealing with tangent space which are of dimension 2. So in the hypothesis, so let us assume this dimension of B to be equal to 2. Dimension of B is equal to 2. So then there exists an orthonormal basis E1, E2 of this B such that if P is equal to XE1 plus YE2, so then QB equal to lambda 1 x squared plus lambda 2 y squared. Our next thing is to show that Q of B is equal to lambda 1 x squared plus lambda 2 y squared. Okay, so this E1 and E2 are orthonormal vectors of P. So if I take the linear span of this E1 and E2, the subspace will be of dimension 2 and dimension of B is equal to 2. So therefore, the subspace generated by this E1, E2 will be exactly equal to B. So therefore, so this E1 and E2 forms an orthonormal basis of B. Okay. Now let us take any vector. So let B belongs to capital B and B is equal to XE1 plus YE2. So this QB, so this is equal to B comma B. which is again equal to b x e1 plus y e2 comma x e1 plus y e2. So this b, it is linear in both coordinates. So therefore, I can write this as x b e1 comma e1 x square b e1 comma e1 plus xy b e1 comma e2 plus xy b e2 comma e1 plus y square b e1 e2 comma e2. So b e1 comma e1, so this is equal to the inner product of a e1 comma e1. So q e1 is equal to b e1 comma e1. This is equal to inner product of a e1 comma e1. And we have taken this lambda 1 to be equal to QE1. So lambda 1 is equal to QE1, which will be equal to the inner product of AE1 comma E1. And lambda 2, so this is equal to BE2 comma E2. And BE1 comma E2, so this is equal to the inner product of AE1 comma AE2, E2, because this A is self-adjoint, so this inner product will be equal to inner product E1 comma AE2, and this inner product is symmetric, so this will be equal to the inner product of AE2 comma E1. So therefore, this is equal to again BE2 comma E1. Therefore, this Q of B, or if I just write down Qx E1 plus Y E2, so this will be equal to lambda 1 x square plus twice B xy plus lambda 2 y square. So where this B is equal to capital B E1 comma E2. So we have this thing, and by the lemma, it follows that this B is equal to 0 because QB is maximum at E1. So since Q is maximum at E1, so which corresponds to 1 comma 0. So therefore, by the lemma, B is equal to 0. So therefore, we have showed that, so QB is equal to lambda 1 x square plus lambda 2 y square. Okay. So this we have shown. And now, again, if I take this QB, which is equal to lambda 1 x square plus lambda 2 y square. So this is always greater than equals to, so lambda 1 is the maximum. So lambda 1, it will be always less than equals to lambda 2. So it will be, sorry, lambda 1, it will be always greater than equals to lambda 2. So we have now, so this lambda 1 x square plus lambda 2 y square will be greater than equal to lambda 2 x square plus y square, and x square plus y square is equal to 1. As x square plus y square is equal to 1. Since B is equal to x e1 plus y e2, it belongs to the circle. So therefore, x square plus y square has to be equal to 1. So this shows that, so this lambda 2 is minimum of QB such that norm of B is equal to 1. Okay. So using all these things, we have this following theorem. Let A B to B be a cell adjoint operator. So again, dimension of B, I have to take it to be equal to 2. So then there exists an orthonormal basis E1, E2 of B such that A E1 is equal to lambda 1 E1 and A E2 is equal to lambda 2 E2. So where lambda 1, lambda 2 respectively are maximum and minimum of the quadratic form QB equal to the inner product AB with B, where this B, it belongs to the circle. Okay. So what is the proof of this theorem? Okay. So by the previous proposition, so there exists an orthonormal basis E1, E2 of B with QE1 is equal to lambda 1 and QE2 is equal to lambda 2. So lambda 1 is the maximum of QB, norm of B is equal to 1, and lambda 2 is the minimum of QB, norm of B is equal to 1. So we know that this B E1 comma E2 is equal to 0. So 0 is equal to B E1 comma E2, which is again equal to the inner product of A E1 comma E2. So this shows that So AE1 is orthogonal to E2. So therefore, this AE1, it has to be equal to alpha E1 for some alpha belonging to R. Okay. Now lambda 1, so this is equal to the inner product AE1 with E1, which is again equal to the inner product alpha E1 comma E1. So this is equal to alpha inner product E1 with E1. So E1, it is a unit vector. So inner product E1 comma E1 is 1. So therefore, this will be equal to alpha. So therefore, alpha is equal to lambda 1. So AE1 is equal to lambda 1 E1. So therefore, this lambda 1 is an eigen value of this A with eigen vector E1. Okay. So similarly, so 0 is equal to BE2 E1, which is equal to the inner product A E2 comma E1. So this implies that E1 is orthogonal to AE2. So therefore, AE2 will be equal to some beta E2. So beta belongs to R. And lambda 2, so this is again equal to inner product AE2 with E2. So, so this will be equal to beta E2 inner product with E2. So this will be equal to beta. So therefore, what we have, so this AE2 is equal to lambda 2 E2. So again, so this lambda 2 is an eigenvalue of A with eigenvector E2. I'll stop here.